Welcome to Sir Majesty Easy World Science channel. Today I will be handling acid-base theories. Acid-base theories are actually different ways of defining acid and bases by different authorities. In real sense, they are not actually a theory. So we will focus on the three common acid-base theories, which are the Arrhenius acid-base theory, Bronsted-Lowry acid-base theory, and G.N. Lewis acid-base theory. We will also take a look at the Lux-Flood acid-base theory, the definition, and also the solvent system. First, in the number one is the Arrhenius acid-base theory. First, I want to correct an impression. Among all the theories I will be handling, none is the best one and the most suitable definition of an acid. No, rather, each one is correct depending on the chemical situation at a certain chemical reaction and a certain situation and conditions. One definition is correct, and each of the definitions you'll be seeing have its own limitations. Therefore, we will discuss the theories and also tell you the limitations of each theory in each case. So Arrhenius acid-base theory, if they tell you what is an acid, I know what comes to your mind is burning sensation, something a kind of corrosive, and this is what comes to mind when you mention acid. Equally, bases are also corrosive, and you see it as poisonous compounds. But I want to correct that impression. Some drugs we take are equally acids. Some foods we take every day contains natural acids. Like if you take any fruits are natural sources of acids. So acid cannot be all that our enemy at all cases. So there is no theory that defines acid as a poisonous and dangerous chemical. But generally, acids will be handled very carefully because most of them are dangerous. So vitamin C is an acid. Even when you take that drug vitamin C, we call it ascorbic acid. When you drink milk, there is a sort of acid there called lactic acid. So acid is our friend, acid also is our enemy. So do bases are. So by definition, Arrhenius told us that acids are substances that dissociate in water to produce hydrogen ion as the only positive ion, or that dissociates in water to produce hydroxonium ion or hydronium ion as the only positive ion, while bases are substances that dissociate in water to produce hydroxyl ion as the only negative ion. Now, this man focused on acid-base reactions as only something that happens in a aqueous system. In non-aqueous solution, Arrhenius didn't tell us what happens in acid-base reactions. So he saw acid-base reactions as the one that is taking place in the presence of water, and that is why the definitions is attached to water. The one that dissociates in water to produce hydrogen ion as the only positive ion, it is called an acid. The one that produces hydroxyl ion as the only negative ion, that is what he called a base. Therefore, his limitation is that he couldn't account for acid-base reactions in non-aqueous systems, in non-aqueous solutions. That acid-base can go outside aqueous solutions. So, according to this man, if you have HX or HA to give you H plus and A minus, this is the only positive ion, and this justifies automatically an Arrhenius acid. Reason is because this is the only positive ion and there is no other positive ion. And then if we have such compound as we have XOH dissociating to give you X plus OH minus, this is automatically Arrhenius base. Reason is because the only negative ion is OH. So hydroxyl ion as the only negative gives you base, which means according to Arrhenius, bases are the sources of hydroxyl ion that adds hydroxyl ion, more hydroxyl ion to water, and acids adds more hydrogen ion to water. Since his definition is based on aqueous solutions, we need to understand that water is self-ionizing, meaning water ionizes naturally into hydrogen ion and hydroxyl ion. So an acid is anything that will increase the concentration of the hydrogen ion in water, and it is meant to understand that in water there is equal concentration of hydrogen ion and equal concentration of hydroxyl ion. Therefore, Arrhenius acid is anything that will increase the concentration to dominate that of OH, while base is anything that will increase the OH of water to dominate that of hydrogen ion. That is what Arrhenius see as a base. So I've told you the limitation to this is that he only accounted for acid-base reactions in aqueous solutions. What if there is no water? Must it be in the presence of water that we can say that something is acid? If you use most indicators like litmus, it rhymes with this man. Litmus cannot work well in any gas or in any substance when it is dry. Without water, no gas is acidic or basic. So, young man in this situation looks correct in the terms of using litmus paper as acid-base indicators. Now, which means that when we come to the reality, we can now give examples of an acid that conforms to Arrhenius theory and examples of bases according to Arrhenius. So if we call such acid as HCl, we remove now A to be specific this time around, it will give you hydrogen ion plus chloride ion. If you say H2SO4, it will give you 2H plus tetraoxosulfate 6 ion. These are the only positive ion, and this makes this acid, Arrhenius acid, Arrhenius acid, Arrhenius acid. That's this AA I'm using here. Now, in this case, he also told us that it can also be producing hydroxonium ion in water, which means we can increase HCl, dissociating in water. The situation is that this must be aqueous. That's the meaning. This will also be aqueous. This is ionic. So only ionic reactions where we can obtain acid-base reactions. We cannot get them outside ionic reactions. So anything that doesn't dissolve in water cannot be either a base or an acid, according to him. But that's not true. There are some situations where substances that don't dissolve in water can act as an acid, okay, depending on different authorities. So when we say HCl, it will now dissociate to give you hydroxonium ion and then the chloride ion. By so doing, this is still an acid because the only positive ion is either hydrogen ion or hydroxonium ion or hydronium ion in this situation. Now, we take a look at the bases according to him. If you see a situation like this, we have sodium hydroxide. This is a base. This is also forcing bases to be source of OH. So anything that doesn't have OH, according to Arrhenius, is not what? A base. And anything that doesn't have hydrogen ion is not an acid. One good thing about this definition is that it tells us the dissociation constant, because since he told us any substance that dissociates in water to produce hydrogen ion, this theory tells us the dissociation constant of acids, which is used to measure the strength of an acid. From the dissociation constant of an acid, you can say whether an acid is actually a strong acid or a weaker acid. Okay, so let us see the dissociation constant of a monobasic acid. We have this such acid as HA. When it dissociates to give you H plus A minus. If you take the normal, if this should be an equilibrium constant, you take this place as the concentration of the product all over the concentration of the reactants. The ionic products here is now raised to power 1 because there is only one here, as it, then multiply by A minus also, or divided by the concentration of HA. So this is actually the ionic product. In this situation, one can introduce what we call pKa. Well, I can now clean this to be the Ka, that is the dissociation constant. Acid dissociation constant is just this. Most times you can include water, but the question there is that since water when it is very, very dilute, water concentration remains constant such that there is equal hydroxyl ion and equal hydrogen ion. So water will have no much strong effect. Like if you can say HCl, like I wrote before, to give you water, it will give you H3O plus Cl minus. So the acid constant, the dissociation constant of the acid is just normal. We have the product here, H3O plus raised to power the coefficient, there is no number here, multiplied by the chloride ion concentration raised to power the coefficient, divide by also water raised to power the coefficient, and also divide by the HCl raised to power the coefficient. But in dilute solution, the concentration of water remains almost constant. Therefore, we can neglect this water effect. Okay. Now, I want to introduce you to what we call pKa. That is getting the negative log or the inverse log of the dissociation constant of an acid. Acids that are strong acids have low pKa. That is, the negative logarithm of the dissociation constant of strong acids gives us a lower value, while the pKa of weak acids are higher. So in exam, if they give you pKa of acids, if it is a high value, know that such acid is likely going to be a weak acid, meaning it has a low dissociation constant, such that when if take a good example of what I'm saying here is, if the dissociation constant of a given acid A is 4 and another acid B is 2, the inverse of 4 is lower than the inverse of 2. That's why pKa is actually, if you have that this is our Ka, which is the dissociation constant of an acid, our pKa will now be the negative log of it will now be pKa will now be log of Ka, the inverse of it, by 1. That means 1 over Ka, which also implies that pKa is equal to negative log, use marker the right way, negative log of Ka to base 10. And now I told you that when the pKa of an acid is low, it shows that such acid is a strong acid. When it is high, it is a weak acid. So acid dissociation constant is the measure of the dissociation, that's the ability of the acid to make the hydrogen ion available. As they dissociate in water, their strength, how much of the hydrogen ions were they able to add to water to increase the acidity. That is what we mean by pKa. Take for example, when we go to the halogens, the hydrogen halides, which are all acids in aqueous solutions, of course. So we have fluorine, chlorine, bromine, iodine. Their hydrogen halides is you put hydrogen there, or remember, because we are discussing Arrhenius, they will all be in aqueous medium. It has been confirmed that the pKa, what are the pKa value for these acids? The pKa for HF is 3, that of HCl is -7, that of hydrobromic acid is -9, that of hydroiodic acid is -10. If you look at this value, this one have the highest value. The pKa of HF is highest. This is already established. That means that hydrofluoric acid is the weakest among these hydrogen, that's the hydrohalic acids. So HF is a weak acid, although it has a very strong corrosive effect. It's one of the most corrosive acid, but it's still a weak acid. From this value, it shows that hydroiodic acid is the strongest among these 4 acids, followed by HBl, because -10 is the least value. So if you press the log, the negative log of the Ka of hydroiodic acid, it will give you 10 -10, while this one will give you 3. So the higher the pKa value, the less acidic and indirectly the more basic, of course, or the weaker the acid is. So that is it for the Arrhenius acid base theory. I repeat that according to this theory, he saw anything that adds more hydroxyl ion to water as a base and anything that adds more hydrogen ion to water as an acid. And he saw acid base reactions as a a reaction that only occur in aqueous situations. But this reaction cannot proceed. In other solvents, water is not the only solvent that is possible. And now, with this means that acid-base reactions automatically ends up reacting hydrogen ion and hydroxyl ion to give you water. So in this case, I will demonstrate the reaction between acid and base, so that you see the ionic equation of all the acid-base reactions in aqueous condition automatically ends up being the same thing. Name a base. One can say KOH plus what? HCl. What will it give us? It will give us potassium chloride, which is a salt, and then water. Therefore, remember, this is going to be aqueous, this aqueous, and this is now liquid. The equation is balanced. According to Arrhenius, this is a base, this is an acid, because this is the source of OH, this is source of H, and they end up giving us what? Water. So let us see the ionic equation. In writing ionic equation, you dissociate aqueous solutions. Don't dissociate the three states of matter, meaning if you see any of the reactants or product in solid, liquid, or gas, you don't dissociate it. So this is aqueous. We have K plus OH minus, okay, then plus what? H plus Cl minus to give us K plus Cl minus. Remember, if there is 2 here, I'll put it here. If there is Cl2 at the back of this, I'll put 2 here. So as you are dissociating, you are also balancing the atoms, the charges, the ions will be also balanced. Plus, this is liquid. Remember, I told you don't dissociate the 3 states of matter. Because it's liquid, I will repeat it. So what do I do next in ionic equation? I'll cancel species that are the same and equal on both sides. I'll pick K plus. Do I have K plus? This is the reactant side. I have only one K plus. Check product side. I have it. So, and that is it. They will strike each other. Then OH is on this side. Do I have another OH on the product side? There is no OH. So OH survives. Hydrogen ion is here. Do I have anyone here? No. Hydrogen ion survives. Chloride ion is on the reactant side. Chloride ion is on the product side. Therefore, I'll strike them. So what survives at the end is the OH plus H plus, giving you water. Even if I take a look at another neutralization reaction, let's say H2SO4 plus sodium hydroxide, I'll still end up getting this. That is why, according to Arrhenius-based theory, you can define neutralization as the reaction between hydroxyl ion and hydrogen ion to produce water, or reaction between hydroxonium ion and hydroxyl ion to produce water. Let us see if this is true. What are the products gotten? Remember, it will give us salt and water because it's aqueous. But when we go to Bronsted-Lowry, we can see where another solvent is involved, not only water, okay? A salt and another solvent is formed. H2SO4, this is aqueous to give us sodium tetraoxosulfate 6 plus water. Okay, to write the ionic equation, what must we do? Remember, this is aqueous, this is also liquid. We follow the same step. This is hydrogen, we write H plus, and this 2 you put 2 behind, then plus okay, this is not balanced. I have to balance the equation first. Balance the molecular equation before writing the ionic equation. Hydrogen is 2 balanced, sodium is 1, sodium is 2, so I have to do justice to that. I'll put 2 there. That makes hydrogen now on the reactant side 4. I'll put 2 here. That balances the equation such that the mole ratio of acid to base is 1:2. So let's go. We now have H plus, you put 2 here, plus tetraoxosulfate 6 ion. There is no 2 here, so this survives, plus Na, you say 2Na plus because of the 2 here, plus 2OH minus because of the 2 here, to give us 2Na plus because of these 2, plus only tetraoxosulfate 6 ion. This 2 doesn't affect it. Then plus 2H2O. Do what we did here. Ions that are alike and equal should be striked out. Do we have 2 hydrogen ions on the product side? No, so it survives. SO4, sodium. So what survives at the end? 2H plus plus 2OH minus to give us 2H2O. They are in the same base, which means 2 can still cancel. We found out that it's the same ionic equation that we got here that we also got here. So Arrhenius is actually consistent in his definition of acid and base. Now, the next theory should be the Bronsted-Lowry acid-base theory.